So here in the middle-ish of my screen, I am going to draw a complex plane. I'm actually going to move that over a little so that I have enough room to do some stuff here. All right. So in our complex plane, our horizontal axis is where real numbers belong. And our imaginary axis is where imaginary numbers belong. And when we have a number that has both a real and an imaginary component, we have a complex number. And we can express these complex numbers in multiple different ways. So over on the left-hand side here, we're going to talk first about rectangular complex numbers. So a rectangular complex number, A, I'm going to denote complex numbers as a variable with a bar over it because I don't physically possess the capability of bold facing what I write. So if you look in a textbook or, I don't know, a Khan Academy video or some kind of crap like that, you'll typically see complex numbers represented as bold-faced variables. I'm going to say that a complex number A will have some real component, alpha plus j beta, where alpha is the real part of complex number A, and beta is the imaginary part of complex number A. All right. So if I were to graph this, assuming both alpha and beta were positive just for the sake of argument, I might have something, I wish I could draw a straight line here, like so. And therefore, the projection of complex number A onto the real axis is alpha, and the projection of complex number A onto the imaginary axis is beta. So before we move along from here, I want to talk about J, all right? J is defined to be the square root of -1, all right? In your pre-calculus class, I believe, you likely learned that the imaginary operator, the square root of -1, was I. Well, in electrical engineering, we can't use I because I is current. That would just be wildly confusing. So we have adapted J. That is literally the entire reason we use a different symbol. We use I for too many other things, okay? So J is the square root of -1. Many of your calculators can only deal with J to certain powers. So I want to talk about the different powers of J, and I'm going to develop a little table here, all right? So here in the middle, I'm going to put J to the 1. And this is obviously just then J, which is the square root of -1. So if I have J to the second power, this is J multiplied by J, which is -1. J to the third power is J multiplied by J squared, or -J. J to the fourth power is J squared times J squared, or +1. Does all of that make sense? Let's start there. Based purely on that original definition that J is the square root of -1. So J to the fifth would be j times j to the fourth power, which is just j. And effectively, we're going to see that this cycle then repeats, right? So if we ever want to know what, let's say, j to the 13th power is, j to the 13th power is the same as j to the 9th power, which is the same as j to the 5th power, which is the same as j to the 1st power. We can just subtract 4 from the exponent because it cycles through those 4 different values over and over and over again. All right. We can do the exact same thing going backwards, right? J to the 0 has to be 1 because anything to the 0th power is 1. So j to the minus 1 is 1 over j, which is the same as negative j, which is exactly what j to the 3 was, right? So it's still doing that exact same cycle. Because if we said j to the 3, and then we subtracted 4 from that exponent, we'd have j to the minus 1, and they have to be identical. So I'm just trying to illustrate that it cycles back the other way too. So j to the minus 2 is negative j times negative j, which is positive j squared, which is negative 1. And j to the minus 3 is just j, and so forth. I'm saying all of this again, you will have homework problems and a problem on your in-class assignment and all that kind of crap that has j to a weird power that is an integer, and your calculator, depending on which one you have, will crap itself unless you bring it back down to somewhere between j to the minus 3 and j to the positive 3. All right, so do we all understand what the imaginary operator j is doing? All right, so I'm going to scroll back up here. I've plotted my complex number a on this axis. I can represent it in a couple of different ways. All right. So the next type of complex number that we're going to talk about is the exponential complex number. So I can say that this vector, two-dimensional vector, complex number A, has a magnitude that is just capital A, no bar over it, and it forms an angle, theta A, with the real axis, such that my complex number A could also be expressed as A e to the j theta A. All right. A, actually, I'm going to change this slightly to make it a little bit more clear here. The magnitude of the complex number A. All right. So how would we determine the magnitude of this complex number? Anybody have any thoughts? Exactly right. Good old Pythagorean theorem. Square root of alpha squared plus beta squared gives us our magnitude. And to find our angle, there are a multitude of different ways. The one that I am going to talk about very specifically is the inverse tangent or arctangent of the imaginary part, sorry, this should be beta, divided by the real part, alpha. Okay. Now I want to point something out here. So if you have your calculator, I'm going to draw another complex plane here just real quick. And let's say that we have a complex number A that is 4 units in the real direction and 3 units in the imaginary direction. And we have a complex number B Pardon?
For the A, that's J times 3.
Yes, J times 3. Complex number B will be negative 4 units in the real direction minus J 3 units in the imaginary direction. So I would like for you guys to tell me what this angle theta A is in degrees, please. Use your calculator, obviously. Don't do this crap by hand. I don't even know how you would do this crap by hand if I'm being entirely honest. Thirty-six 36.87 degrees. Okay, now please tell me what the angle theta B is. Understanding here that theta B should be this angle. If I take the inverse tangent, trying to trick people, Ian. So if you literally put in -4 for alpha and -3 for beta, what do you get? 36 point blah, blah, blah. 36.87 degrees, positive L. Are these two angles the same? Catherine, what's your question? Correct, you do not. So you only want the imaginary part of the number. So J is the operator that tells you what part is imaginary, but you don't actually include that. That's a very good question, then. So we get 36.87 degrees for angle theta A, which absolutely makes sense because an angle of 36.87 degrees lies in quadrant 1, where we can see very easily that our complex number A actually lies. If we take the arctangent of -3 divided by -4, we get that exact same value of 36.87, but we can see very clearly that our complex number is supposed to lie in quadrant 3. So the problem that we are having here is that our calculator cannot distinguish +3 divided by +4 and -3 divided by -4 because the negative signs cancel each other out. So when we're doing this by hand, we can come into quandaries like this, where we think we're getting the right answer because the calculator historically knows what it's doing. But in this specific case, it does not. We'll actually find that it's going to give us the wrong angle anytime our complex number lies in quadrant 2 or quadrant 3, okay? Because the arctangent will only return values in quadrant 1 and quadrant 4. I say this because when you actually start to learn how to use the complex number settings on your calculators, all of this will be taken care of. But if you're trying to do this kind of crap by hand, or heaven forbid, you haven't followed my instructions and bought a not shitty calculator by this point in the class, you're gonna have to deal with this crap all the time, okay? So I implore you, if you have not yet purchased, I take that back. If you are still using a TI-30, stop, please stop. You're gonna cause yourself and me so many headaches. Spend the $12 or whatever and buy a better calculator. And if you literally can't afford it, come to me and I will give you one. I have like 5 of the damn things, okay? All right, now, okay. So I'm going to erase some of this stuff because I'm kind of running out of room here. There's more things that I want to talk about, but I just wanted to get that in the mix, as it were. So we have learned two equivalent representations of complex numbers to this point, the rectangular form and the exponential form. I'm about to introduce a third, and it is what's called the polar form. And it is overwhelmingly what electrical engineers use. All right. So a polar form complex number A is the exact same thing as an exponential form complex number A, except that out of sheer laziness, we ignore the e to the j bit and just say that it's magnitude with some particular phase angle, theta A. It carries literally the exact same information as the polar form, but it's less work to write down, which is why it was invented. Okay. It is overwhelmingly what we will use in this class because it carries all the information that we need. Effectively, what's happening here, and we'll talk about this very extensively we'll talk about it some on Friday and very extensively on next Monday, is we are suppressing the frequency component of our complex number when we use the polar form. I know that that means absolutely nothing to you all right now. I promise by Friday it will mean a little bit of something, and by Monday it will be clear, okay? So the polar form and the exponential form, again, cannot state this enough, literally represent the exact same quantity, just expressed in slightly different ways, all right? Your calculator, by the way, many of you probably don't know this yet, but you will by the end of today's lecture, likes polar form complex numbers and rectangular form complex numbers. And if I'm being honest, it probably doesn't even know what the hell an exponential complex number is, okay? Your calculator absolutely has a button that you can press to give you the imaginary operator J, and it also has a button that you can press to give you the angle operator, which specifies this is the angle of a complex number, okay? So we are going to use polar form over here on the right-hand side, rectangular form over here on the left-hand side. Since these guys represent the same thing, the magnitude of complex number A is still just the square root of alpha squared plus beta squared. And the angle theta A is still simply the arctangent beta over alpha. So we have learned how to express exponential and polar form complex numbers in terms of their rectangular components. It may be useful for us to convert the other way back around. So we could say that alpha is simply the magnitude of A times the cosine of theta A, using good old simple trig identities. And similarly, beta is the magnitude of A sine theta A. So now we have a bilateral transform. We can go from rectangular to polar or exponential, and then we can go from polar or exponential back to rectangular as is necessary. And when we get into doing mathematical operations with these, I'll make it clear why sometimes it's easier to do some types of operations in polar and other types of operations in rectangular form. But before we get to that, I want to introduce something that I believe will actually be new for the overwhelming majority. And that is the concept of the complex conjugate, okay? So what the complex conjugate operation does is it simply flips a complex number about the real axis. So if we have a complex number A that lies in quadrant 1 then we will have a complex number A with an asterisk, where that asterisk, I can't pronounce asterisk today for whatever reason. I apologize. I feel like I'm going real hard on one of the S's there. Denotes the complex conjugate operation, all right? So what is the difference between A and A conjugate? Anybody, can you tell me from the graph? This negative imaginary component in the rectangular form. What's the difference between the polar forms? The angle is negative now. That's it, right? So that's all that the complex conjugate operation represents. So we could say that A conjugate is equal to alpha minus J beta. So all we've done here is simply flip the sign on the imaginary part, and flipping the sign on the imaginary portion is exactly identical to changing the sign on the angle. So I'm at a crossroads here, because what I want to do right now is to show you what a complex number multiplied by its complex conjugate gives you. But in order to do that, we have to understand how to multiply complex numbers. So I think first we will introduce mathematical operations using complex numbers and then circle back around to that. So let's start with addition. Let's say that I have a rectangular form complex number A that is lowercase a plus JB, and I have a complex number B that is lowercase c plus JD. If I want to add complex numbers A and B, simply add them, right? So this would be A plus JB plus C plus JD. I can see that the real parts add together. So I would have A plus C plus J, B plus D. So the real parts add together and the imaginary parts add together. So for those of you that have had Physics 201, which should be all of you, this is just like adding Cartesian vectors. We add the part in the real directions together, we add the parts in the imaginary directions together, which is the exact same thing that you did when you added the X components of vectors together and the Y components of vectors together to get a resultant vector. It is literally the exact same thing. And you can absolutely use the graphical method of adding complex numbers tip to tail and all that kind of stuff to figure out where the resultant is going to be and all that jazz. So all those handy dandy vector addition and subtraction tricks that you've learned in your math 243 class and in your physics 201 and all that kind of crap absolutely can be used here. Okay. So addition is very, very straightforward using rectangular complex numbers. I don't even know how to begin to do it using polar form complex numbers. So just if you're going to do it by hand, use rectangular form complex numbers. Subtraction is also very straightforward, right? So let's say that we have the exact same complex numbers. A is equal to lowercase a plus JB, and B is equal to lowercase c plus JD. So subtraction is just addition, but now there's a -1 factor, scalar factor involved, right? So this is going to be A minus B looks like A plus JB minus C plus JD would be A minus C plus J B minus D. So subtraction works in the exact same way that factor combination, subtraction, and all that kind of crap work as well. Hopefully, addition and subtraction are very straightforward. I hope I'm boring you to tears right now. That's my intent. Multiplication is where things get a little bit different. So if we have those same complex numbers, A multiplied by B, and I want to be very clear, okay? I could put a dot in the middle of those guys, and that would mean multiplication. I could put a cross in the middle of those guys, and that would also be multiplication. We are not doing cross products and dot products or anything like that in this class. So multiplication is multiple way around, okay? There is no such thing as a dot product of complex numbers, nor is there a cross product of complex numbers. So we're going back to old school third grade multiplication, all right? So when I multiply complex numbers A and B, sorry, this should be C plus JD. I have, in rectangular form, I wind up having to FOIL all this crap out, right? So I'm going to have A times C plus J A times D plus J B times C plus J squared B times D, which is going to be the same as A times C minus B times D plus J A times D plus B times C. That minus sign comes from the fact that J squared is -1. All right. So we have two real components, the part that has no J's whatsoever and the part that has J squared. And then we also have, and those get combined. And then we have two imaginary components, both the bits with a J in front. We combine those together. Okay? So multiplication in rectangular form is tedious, but it is doable. Now let's look at multiplication in polar form, or excuse me, exponential form explicitly, okay? Polar form is going to throw away too much information, so the process will work that we're going to develop from it for understanding why it works really needs us to look at our exponential forms. So in an exponential form, we would have our complex number A would be the magnitude of A times e to the j theta A, and our complex number B would be the magnitude of B e to the j theta B. So when I multiply complex number A by complex number B, this looks like the magnitude of A e to the j theta A multiplied by the magnitude of B e to the j theta B, which is simply the magnitude of A multiplied by the magnitude of B e to the j theta A plus theta B. So multiplication of exponential form complex numbers is just you multiply the magnitudes and you add the angles and you get the result. Obviously, the exact same thing happens when you work with polar form complex numbers, because again, polar form complex numbers are just exponential complex numbers written lazily. right? So is everybody okay with multiplication in both rectangular form and exponential form? And if you have a question, feel free to ask. Benjamin.
What happened in the multiplication in the rectangular form? What happened to the j squared ED?
Okay, so earlier, we wrote down a table that had j to different powers. Would you look at your, do you have the table written down? J squared is a -1. So that's why I got rid of the j squared and lumped that in with the real number terms, right?
Oh,
So that negative BD is actually plus j squared BD. Does that make sense?
yes.
All right. No problem. Any other, this crap is going to be confusing to an overwhelming majority of you because you haven't done this complex gobbledygook like I have for years and years and years. All right. So questions are good. Yes, sir.
Going back to polar form, what was the symbol you wrote down?
I'm going to scroll up because you said polar form.
Yeah.
What symbol do you think I am?
Less than.
Okay. No, that is not less than. That is the angle operator. So what that means is that the polar form complex number has a magnitude and an angle, and it is literally defined magnitude, angle operator, angle. So that's literally just saying you have a magnitude, so you go out so long on the axis. Let me try to draw this. So one way to think about this, you would go out, let me do it in blue, a units along the real axis. And then once you get out to the magnitude, then you just rotate by that angle. And that gives you your complex number so that it is formed by that length, A, magnitude, and that angle, theta. So again, it carries all of the information that the exponential form represents. It's just a shorthand notation. Okay. All right, any other questions to this point? We still have division and then multiplying by conjugates to do, which is actually going to get rolled up into the same thing here. Any other questions or comments? All right. So, I don't think I have enough room there, so let's do division on this next page. So division in rectangular form is troublesome, okay? Not impossible by any stretch of the imagination, but it can be annoying. So if we have some complex number A is equal to A plus JB, and some complex number B, which is equal to C plus JD, then A divided by B in and of itself is actually extremely hard to do, okay? So what I'm about to do here is going to seem weird, but I'll explain it as I'm doing it, all right? So if I want to divide numbers, divide rectangular form complex numbers, what I'm going to do is I'm going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. And so what I mean by that is I'll have B conjugate here divided by B conjugate here. And so my operations here, I would have A plus JB. What's the complex conjugate of B? C minus JD. Divided by C plus JD times C minus JD. Let's work on the denominator first, okay? Because this is what I was going to get at a little while ago. I'm going to have C times C, so that looks like C squared, Then I'm going to have minus j CD. Then I'm going to have plus j CD. And then I'm going to have minus j squared d squared. So before we look at what's going on at the numerator at all, let's simplify this guy. Obviously, minus j CD and positive j CD cancel each other out, right? What's that minus j squared d squared really look like? Minus negative d squared is plus d squared, right? So we're going to wind up having just c squared plus d squared in the denominator. So when we multiply a complex number by its complex conjugate, we get rid of all of the imaginary parts. We wind up with just having the magnitude of that complex number squared. So as a quick identity down here, a times a conjugate is just the magnitude of a squared. And that's incredibly easy to prove using exponential form complex numbers. I encourage you all to do it. We're going to use that identity multiple times in this class. All right. Now let's go back and revisit that numerator. We're going to have a times c minus j AD plus j BC minus j squared BD, which is going to look like a times c plus b times d minus j a b minus bc. So as I said, division using rectangular form complex numbers is absolutely doable, but it's a pain in the butt, okay? The main reason that I introduced this is because sometimes we are going to utilize that form to make things a little easier on ourselves, okay? The overwhelming majority of the time, we will do it using exponential or polar form complex numbers, where if we have a is equal, sorry, not the magnitude, my apologies. Magnitude of a, e to the j theta a, and a complex number b is equal to the magnitude of b, e to the j theta b, a divided by b is just the magnitude of a, e to the j theta a, over magnitude of b, e to the j theta b, which is simply the magnitude of a divided by the magnitude of b, e to the j theta a minus theta b. So in polar form, division is really easy. You take the ratio of the magnitudes and then you subtract it, or take the difference of the angles. So it's the exact opposite of multiplication. In multiplication, you multiply the magnitudes and add the angles. Division, you divide the magnitudes and subtract the angles. So very easy and straightforward to do in polar form. So that's why the overwhelming majority of the time, I would suggest that you do multiplication and division using polar form complex numbers. Let me walk that back a moment. If you're doing it by hand, you should do multiplication and division using polar form complex numbers, and you should do addition and subtraction using rectangular form complex numbers. I made that caveat there if you're doing it by hand, because your calculators are wonderful things and they don't give a crap whether you put complex numbers in as rectangular form or polar form. It can mix, match, and do all that kind of good math stuff. Okay. So that is our lecture for today. Anybody have any questions, comments, or concerns? Skylar?
Are we gonna apply this to like circuits and stuff?
Absolutely. So,
I know the test is like.
no, so the test is not going to be just, haha, you signed up for a math class. Absolutely not. No. So what we're going to do on Friday is we are going to do an introduction to sinusoidal analysis, where we actually use sinusoidal functions to analyze our circuits. And we are going to find out in a very short amount of time that that is a huge pain in the butt. Okay. It involves lots of pesky calculus and several trig identities and all that kind of good stuff, which make it just a royal pain to analyze even the most simple of circuits. I am going to then introduce you to what is called frequency domain circuit analysis, where we will represent all of those pesky sinusoidal signals that gave us so much trouble as complex numbers. And then we get to use this complex math to effectively turn all of our calculus into algebra, therefore making everything not trivial, but definitely way less of a pain in the butt. Okay, so this isn't just a, let's introduce you guys to a whole bunch of math for no reason. This is going to be integral to you understanding what the hell we're doing for literally the remainder of the class. Okay. I think I'm going to spend probably 30 to 45 minutes working a 3-element problem on Friday to show you just how terrible working these things in the time domain is.